right, so here's the second half of chapter 20, where we're talking about the differences between voltaic cells or galvanic cells and electrolytic cells. So voltaic is the same thing as galvanic. So they're the same thing. So don't get confused with them. Not galvanic. That's something different. No, it's not anything, but galvanic. And that's where we talked about where you have a spontaneous reaction, meaning the cathode is being reduced and it has a higher reduction potential. And the anode is being oxidized and it has a lower reduction potential, meaning it flows in a positive remember that E0, E standard potential. It flows in the positive direction, meaning the higher that number is, meaning the less negative.
Okay, fuck it. I guess my audio will never work.
The less negative it is, then the more reduction potential it has, the more likely it is to be reduced. And that's a spontaneous process. But if you have another type of cell that tends to go against the grain in the opposite direction, where the cathode is now being oxidized and the anode is being reduced, or meaning the one with, well, the anode is always being oxidized, but let's just say it this way. If the one with the lower reduction potential is now being reduced and the higher reduction potential is now being oxidized, meaning again the opposite direction of electron flow, we have an electrolytic cell. So it's a non-spontaneous reaction driven by an external current. So it would be driven by a battery or plugging into the wall. So let's say most electronics use electrolytic cells because you need to plug them into the wall, or at least use a battery that was once plugged into a wall or had some electronic source to go through that non-spontaneous reaction to create that electrical current. So here it is in the diagram form. So it's carried out by electrolytic cell. Electrolysis is the type of reaction. It's a process of using electrical current to drive the reaction, right? And that can be either from plugging it into the wall or a battery. Here they have kind of like a car battery looking thing as the external source. So, I mean, it's just the opposite of the galvanic cell. And here's, you want to look at both of them side by side, where on the left we have our traditional voltaic cell, where the left is the anode, and the anode, look at that, is zinc. And if you remember from the standard reduction potential numbers, zinc has a reduction potential of negative 0.76. So it's very likely to be oxidized, not reduced. So I'll put reduction potential equals negative 0.76. So it's likely to be oxidized, which is why it's the anode and why it's being oxidized spontaneously. And the reduction potential for copper is plus 0.34. I think that's right, but I know it's plus something 4. It might be 5.4, but I think it's 3.4. And this is in volts. So then what you do is here you're going to take the reduction minus the reduction potential of what's being oxidized, and you get plus 0.34 minus 0.76, and then you get 1.1. So that's what this voltmeter reads, 1.1, as the electrical potential or the reduction potential between this or in this voltaic cell. But if you have an electrolytic cell, we can't say there's any volts running through it innately. We need a voltage source that's greater than 1.1 volts to bring it in the opposite direction, because we want to outweigh the spontaneous reaction in terms of volts, in terms of energy. We want to supply more energy than the spontaneous direction to make it go the opposite direction, which is what's going on here. And the cathode is now what's being reduced. And you can see that zinc, which doesn't like to be reduced, and copper, which doesn't like to be oxidized when it's with zinc, is being oxidized. And it's on the other side. So that's what that's the differences between them. One's spontaneous and one's not. All right, conceptual question. So which statement is true for both electrolytic and voltaic cells? B, yes, B is correct. Good. So electrons flow from anode to cathode. So yes, whichever type of cell you have, the oxidation is always happening at the cathode, or sorry, at the anode. and the reduction is always happening at the cathode. But which metals are the anode and which ones are the cathode, that varies based on if it's a voltaic cell or an electrolytic cell.
Professor?
Yes.
I'm sorry, but you just explained like something about, so like the cathode with like flows backwards or something like that. Can you just repeat
yeah.
that?
So I think, I want to clarify that. All right. So in our traditional voltaic cell, we know that, remember I said oxidation anode, right? With the vowels, and then reduction cathode, or like A, I think you guys made A comes before C, right? So anode goes to cathode. That's always the case, meaning the anode is always going to be oxidized. The cathode is always going to be reduced. That's a fact. But which metals or which substances form the anode and cathode, they vary based on what type of cell they are. The standard type we learned are voltaic cells. That was all of last class, where we subtracted the lower reduction potential from the higher reduction potential. So we took the bigger number, like the 0.34, we did minus, then the lower number, which is negative 0.76, and we all the time got a positive number. So remember that if it's spontaneous, where was that? If it's spontaneous, E cell is always greater than 1. It's always, always greater than 0. It's positive. That means it's spontaneous, because when you subtract the reduction potentials of the most reduced, meaning the highest, minus the lower one, it's always going to be positive, and that means it's spontaneous. But now we're talking about the anode for this electrolytic cell. What you said, it goes backwards. What actually goes backwards is the standard direction of flow, meaning not from anode to cathode, but from metal to metal. So originally, the electrons would flow from I'm looking at this. I'm like, wait, they're both the same. I was like, no, it's the wrong slide. Here we go. This is the right slide. So originally, they would flow from zinc to copper, right? Zinc is being oxidized. Anode, electrons flow to the cathode. But now it's going from still anode to cathode, but the metals switch. That is the non-spontaneous direction from copper to zinc, which is not favorable. So in order to make that happen, you need to input voltage energy in the opposite direction at a greater voltage than the standard cell in order to get them to move in the backwards direction. So like if someone's running towards you, or if a car is driving towards you and you're driving a huge truck and you slam into that car, the one with the most momentum will move the one with the least momentum. Same thing, but with electrons, right? So yeah, cool physics lesson, throw in there. Well, this is physics also. It's all physics. Oh, so you want to hear something cool? So those of you who are thinking of going into biology, here's a great justification that I tell people. Rifki, yes. So when you subtract them, it would be negative. And what does negative mean? It's not spontaneous anymore for E, for the potential. Exactly. Good. So that means that confirms it. Nice. So here's something that a lot of engineer people like to say. Now, the fundamentals of STEM, I know we're going off topic here, but whatever. The fundamentals of STEM, you have math. Math is the foundation of everything. Like physics came from math, chemistry came from math, biology came from math, engineering came from math, everything came from math. Then, if you apply mathematics to the world, you get physics. Because you can so physics is how matter interacts with one another, or how matter moves, or really what the world is. How the world moves. It's physics. That is all based on math. Now, you can use physics as a basis for, okay, what is the matter that moves? And that's what we're doing. That's chemistry. So physics is the basis for chemistry. Mathematics is the basis of physics. Now, chemistry just tells us what the hell the substances are that are moving around in the by the physical principles that we know about in physics, which is dictated by math or explained by math. Now, though that matter that moves, or that matter that is, what about the matter that's alive, which is the higher level of thinking, the higher level of matter organization? The most complicated things on our Earth are the ones that are alive in terms of their chemical complexity. And that's called biology. And biology is using the basis of chemistry to apply it to our living systems. So if you think about it, so when people say, oh, why'd you choose biochem? And if I want to sound like a smartass, I say, well, because to be a biologist, you need to know and have a fundamental understanding of everything. Because it's not just the chemistry that goes into biology, the reason why our proteins make cancer, the reasons why we can talk. That's all chemistry. And it's also physics, because, I mean, with talking, you have sound and all that stuff, right? So you need to have an understanding of physics. So all the time in my research, half of it is like a lot of physics equations that show up because it's a fundamental part of biology. And then the basis of that is math, where in biology, I don't care what field you're in, you're going to have math all the time. That's the foundation of everything. So if people are like, oh yeah, I'm a mathematician, like I understand the basic, most fundamental principles of everything. All right, can you expand on that? Can you talk about physics? Can you talk about why math is important? Because math as itself is not important. Oh, Rebecca, nice question. So can you show us the research? Of course I can. I'll pull up a presentation after this. I'll pull up like a random presentation I have. And then, yeah, Christina, but the physicists say, if everything is physics, why not just study physics? Well, how are you going to apply physics? Because if you want to think about it, what's the most important thing? Well, that answer varies. But some people think the most important thing is figuring out about the universe. And then what do you need to figure out about the universe? You need all of them. You need physics, you need chemistry, and you need biology. So physics, it doesn't stop at physics. Yeah, so biology, you have to know everything. And then you could think, all right, what is the basis? Yeah, physics are too basic. Yeah, physicists are too basic. Now, then you can answer the question of what's the purpose of biology? Like, what is that the fundamental understanding of? I don't know. I have no idea. We didn't discover it yet. Maybe if you want to talk in like a theological point of view, maybe if you believe in whatever, depends on what you believe in, maybe biology is like our higher level of earthly understanding to understand extra dimensional life or life that could exist on different planes. Maybe that's a segue. Maybe that's the basis of understanding that. I don't know. But yeah, well, human advancement can be anything. It could be physics, it's all of them, human advancement. But anyway, good talk. Cool. Yeah, so I will make up for not being in class by showing you my presentation, showing you a couple of presentations that I've looked at I've done during our break. About my research, because it's fun to talk about. Okay, so we did that. We talked about electrolytic. Okay, good. I'm glad you're excited. Awesome. Electrolysis of pure compounds. So generally, I mean, you don't have to really remember this for exams, but the cations are generally reduced and the anions are oxidized. That makes sense, right? Because your cations are positive charge, and if they're electrolysis, what they normally want to do is they want to become neutral, right? So to become neutral, you have to gain electrons. So cations are gaining electrons to get to neutral. And anions, to get to neutral, they want to lose electrons. So they're being oxidized. All right, so here's an example of electrolysis of NaCl. And you can break apart Na and Cl into components by electrolysis. So electrolysis, you can break that word apart. That means the breaking apart by current of a substance, electrolysis. Just like hydrolysis, which means breaking a bond and production of water. So a mixture of ions, we kind of talked about this already. So when more than one cation is present, the one that's easiest to reduce was based on the most positive reduction potential. So if you ever have a mixture of any amount of substances and they have reduction potentials, the same thing that we've always learned applies, which is the higher the reduction potential, the more likely it is to be reduced. The lower reduction potential, the more likely it is to be oxidized. And then they talk about, which I don't like that they even talk about this at all, EOX, which is the oxidation potential. Oxidation potential is the inversion of reduction potential. Just you swap the signs. Goes from negative to positive. And then once you switch the signs, the higher it is, the more likely it is to oxidize. But if you want to, I think we should always stick with one of these systems, because if you it's easy to get tripped up with switching signs and adding and subtracting. What am I doing? Reduction potential, oxidation potential. I would say think about everything in terms of standard reduction potentials. That is the information that'll be given the most. And if you have it lower, it's oxidized, higher, reduced. That's it. Here's just some more examples. Another example. I mean, I don't want to go crazy on that because I do want to get to the worksheet and then chapter 21. So here we go. Stoichiometry of electrolysis. And really for any voltaic cell is that the normal stoichiometry applies. So what this means is that, so we know 1 amp is 1 coulomb per second. And something else that may be given to you on an exam is 1 mole of electrons is 96,485 coulombs of charge, which is Faraday's constant, which was shown in the Nernst equation before we condensed it. Now, what we can say is we can use these numbers and our understanding of stoichiometry to solve problems with oxidation and reduction. So let's look at this question. Fairly simple, but let's see who can get the answer. Silver plating uses the reaction Ag plus E equals Ag. So that is a reduction. How many moles of electrons must pass through an electrolytic cell of silver plating in order to plate 3 moles of silver? Yep, 3 moles of electrons. Good. It's all a 1-to-1 ratio. And how do we figure out how many coulombs of charge that gives? So 3 moles of electron is how many coulombs of charge? Good, exactly. Multiply it. Good job, Ahmad. Multiply it by Faraday's constant, meaning 1 mole is that many, 96,000 coulombs. So it would be about 300,000 coulombs, a little bit less than that. Cool. So corrosion. That's the last thing we're going to be talking about here. And what corrosion is a funny word for oxidation. And we've all experienced corrosion, maybe when we were little with our bicycles. If we left our bicycles outside in the rain for months, they would get rusted. Now I think they don't because they're better bicycles than when I was little. But I mean, not just bicycles, but everything. Any piece of metal, you leave it outside for long enough and it'll start to corrode or it will start to rust. Wait, bikes are made of plastic? No way. Or like maybe the high-end carbon fibered ones are like yeah, I think my girlfriend's dad has this like ridiculous racing bike that's like you can pick it up with your pinky and it weighs nothing and it's made of like just carbon fiber. It's insane. But yeah, something like that won't rust. I would feel terrified of riding something like that because like I picture, and also like the wheels are so skinny. If there's one, like we're in Jersey, most of us, like the roads and the sidewalks are not very good. So if you one rock or one little twist, one pothole, like the things that get ruined. It's so light. But carbon fiber is very strong. But I'm just saying, like, usually when I'm in a vehicle, I would prefer the vehicle, whatever type it is, to be heavy than light, because heavy you feel safer. But Rebecca's right. You got to trust the engineer. I mean, you guys are the future of that. Yeah, Matt, in that 15 steel car. Well, I agree, but without the gas mileage, because they had terrible gas mileage. Okay. So corrosion, different types of oxidation. So what's happening here? Okay. So reduction and oxidation with corrosion. Now, when you're oxidizing the metal in rusting, what is being reduced? And the answer is oxygen. So oxygen is being reduced from oxygen gas into its ionic form, whether it be iron oxides, and usually it's iron oxides if it's rusting, or maybe some other type of oxides, silver oxides or whatever. And yeah, Luke, yeah, everyone needs humanities. There you go. You got to know how to write an essay about things that don't matter. Unless you like humanities, then I guess they matter. Oh, PE is totally important. Of course. We got to lift. Okay, so let's just talk about rusting in the diagram. All right, now here's what happens. When you leave the metal outside, the sources of oxygen will get to it, otherwise known as the elements. And these elements are mainly water droplets. Also, the air has some effect, like the oxygen gas in the air, but usually it's the water, because the water comes in molecular contact for the longest amount of time into the iron. And what happens is the water and the iron go through a reaction and they go through redox. The iron is oxidized to iron 2+. The O2 that forms water is then reduced into O2 minus. Or sorry, no, yeah, well, not O2 minus, but O and then a 2 minus charge. And then those eventually go together and make an iron oxide. And this iron oxide is a precipitate, which is the brown rust. So that is how rusting occurs. Are there any questions on that? Okay, so a follow-up question could be, how do you prevent rusting? Well, there's several things you can do. There are anti-rusting paint, anti-rusting different sprays you can put on, but what do? They do one of two things. Well, for preventing rusting, they do one thing. They give either a non-metal surface to your metal, which then prevents the water from oxidizing the metal. Or even better, they make a sacrificial metal plating that, let's say you had like I'm not sure if they have this, but like zinc is the main one to use. But if you had like zinc paint and painted over the iron, your iron wouldn't rust, but your zinc would oxidize over time, because zinc oxidizes a lot more readily than iron. But anyway, so that's our rusting of iron. Now we want to talk about how we prevent it. And we just said one of the ways is to coat the metal surface and keep it from contact, like a paint, right? Or to prevent it from being rusted by putting another metal that's called the sacrificial electrode. That sounds really intense and like really dramatic, like the sacrificial electrode. I don't know, it just feels intense. But it's not. All it means is that you're taking metal and you're taking metal that is very easily oxidized and placing it and plating metal that is not as easily oxidized to make all of the water oxidize the metal coating and not destroy the integrity of the device. Let's say it's a building, or let's say it is a bike. And like, yeah, Rust-Oleum. That's good. Okay, so which of these metals does not act as a sacrificial electrode of iron? Exactly. So, okay, so we have, oh, whoops, I got to put, okay. These aren't, there's a mistake here. All right, we need to see reduction potential. So that's what I meant to do. I forgot to do that. So let's go online and let's look up reduction potential chart. And we need a list. Hopefully this list has manganese. Yeah, I see manganese. Cool. All right. So we need a list. We have copper, magnesium, zinc, manganese. So which one of them is not the sacrificial electrode? So the sacrificial electrode is going to be one that has a lower reduction potential than iron, meaning it's more likely to be oxidized than iron. So which one is not more likely? So which one is higher than iron is what we're looking for. So where's iron? Here's iron 3+ at negative 0.04, but usually it's iron 2+ because for rust, so here's the other one, negative 0.44. All right, so let's see where copper is. So copper is up here. So copper's higher. So that kind of answers our question already. So copper is higher, meaning it's more likely to be reduced. So it's not going to want to be oxidized more than iron does. So that's our answer. Magnesium, where's magnesium? Magnesium's all the way down here. Something you can keep in mind. So Christina, I'd like to mention that you don't have it memorized. That's fine. I mean, you shouldn't. That's way too much. I don't have it memorized. But something that you could know for a trend is that a lot of the group 1A and 2A metals have extremely low reduction potentials because they want to be oxidized a lot. They lose electrons like crazy, right? Because they're group 1A and 2A. They want to lose electrons badly. So look at that. Lithium, potassium, sodium, magnesium, they're all down here. So that's one little thing you can keep in mind for trends. And other than that, there's not really much trend, no trends. And then the standard hydrogen electrode is 0. That's about it. So on an exam, they might not mention that the standard hydrogen electrode is 0, and they might refer to it. So if they say compare to standard hydrogen electrode or compare it to hydrogen reduction, then you just say, okay, that's the 0 point. And everything's in reference to that. So anyway, magnesium's low. Copper, we know is the answer. Zinc, we know is low, right? Negative 0.76. And manganese also happens to be low, negative 1.8. So we know that copper is our answer, not zinc. Go away, zinc. So the book had that, or yeah, Pearson had that. So I'll leave this on my YouTube channel. See if Pearson comes after me. But Pearson, you need to have somebody edit your slides. So yeah, I'm coming at you. Or I'll make a new textbook when I have time. If I ever have time, I'll make a new textbook. So that's it. Copyright. Well, yeah, I don't want to copy this because it's all wrong. So who needs the copyright? Got him. Yeah, I'm going to get copyright strike.